So what we're about to do next is a classical experiment / demonstration. I previously had made what we're about to see like a whole lab that my students would do. I'm moving away from that this year for a number of reasons. In no particular order. One, it's the next thing we would do. Two, I'm about to depart for 6 days. I won't be here Friday. I'm leaving tomorrow morning. I'm going to Big Island for a canoe race and to see my friends over Hilo side and play board games. This particular lab deals with the single most dangerous chemical that I am willing to give you guys. It's sodium hydroxide. It's nothing like dire, but I'm wearing eye protection for safety reasons because this can cause chemical burns, and if you get it in your eyes, it will make you go blind.
Oh, so safe.
I'm already blind. Yeah, you did.
Actually, there is food-grade sodium hydroxide.
I wear gloves.
They put it in pretzels. I need those. And the way that I used to do this, scratching myself with gloves because I just put them on. But the way that I used to do this, I'd give the students a bunch of options for different salts and gravel and stuff that wouldn't dissolve. But the sodium hydroxide is the thing that works. And I'd be like, hey, this is the danger salt. If you use this, you have to wear gloves. You have to, wear eye protection and be careful. But it's the one that works, and the other ones don't. And I wouldn't tell them which one worked. And it would be days of trying to get the thing to work, and it doesn't. And so it's probably better as a demo. So I have here a solution that I've made of sodium hydroxide. I made this in the previous class period. And I have a bit of wire with another bit of wire attached. And I'm going to put the wire in the test tube, and then I'm going to fill up this test tube with the sodium hydroxide solution. Just tap water and sodium hydroxide. And here's the other kind of reason that I think this probably works better as a demo. I would typically end up having to demonstrate this anyway. I ended up doing this next part for a lot of groups. Put the finger over the end and into the sodium hydroxide. And the point here is I want to avoid getting a bubble inside that test tube.
Why?
The reasons will become apparent in a few moments. And I'm going to do the same thing with a second wire. This one, there's just a copper strip. I kind of didn't want to find all the little bits. There's a copper strip, but I didn't want to try to find them all when I was setting this up. So I just grabbed the copper wire, the other one. And I'm going to do the same thing with a second test tube and a second wire. Back. I should probably speed this up in the final cut. There's a bubble. Means I have to do it again. So better. Oh. That pen fell into the sink. All right. So I have this beaker with sodium hydroxide solution, and like these wires are connected, right, through the sodium hydroxide, and there are, you know, these test tubes with there's no bubble. There's a tiny bubble, but that's okay. Barely see it. And I have a power supply over here, and I'm going to attach. Attach the wires to the power supply and then turn it on. And can anyone see what's happening? See? Bubbles. There are bubbles forming.
Is it like breaking it up?
Is it like breaking it up? Maybe. There's a bubble forming. There's a bubble forming. What are the bubbles? What are the bubbles? Air. Is it air? Okay, so here, does everyone agree that there's air in this here test tube here that we melted so nicely? Everyone agrees? Air? All right, so I'm going to do, there we go. I'm going to do a splint test with air. I have a chopstick here. I'm going to set it on fire. Set it on fire. Set chopstick on fire. And here's what happens with air. It goes out pretty quickly, right? And it goes, you know, like as it goes into like the fresher air at the back, it kind of lights back up, but it eventually just goes out completely. And it doesn't do anything noteworthy or special, right? Okay, the bubbles have grown a little bit. I'm going to pause. Ooh, we have 18 minutes to low tide. I'm going to pause this. I've closed this, and I have a ruler here, and I want to measure. I want to measure these bubbles. This one is, I'm going to call it 3.5 centimeters. And this one is 1 3/4 centimeters. Here we see why we needed there to be not a bubble, because we're going to measure them. We measured the bubbles that formed, and if there had been a bubble, how do we know what was our starting bubble and our ending? Like the bubble needs to not have a starting bubble in order to have an act. And the
couldn't you just measure the first bubble?
Are you supposed to be recording this?
I am.
Not.
It's not. Oh no. I'll have to do it again. Oh well. Okay. He's recording. This is recording.
Oh, here he is.
So we have to share that with. It's not as good. But, all right. I can record it. Okay, here we go. So we have the bubble that's at the negative terminal is twice the size as the bubble at the positive terminal. Because it's going twice as fast. It's formed twice as fast.
But why?
But why? Why?
Science. Wait, which one did you say was fast? Bigger? Negative?
Negative terminal. Bigger bubble.
Did they have more energy? Negative?
No, it's like a circuit, right? So it's like the same amount of energy at either side.
The things you did, like the copper and stuff?
So what we're going to do in a moment, after we get enough bubble, is we're going to do the splint test again with each bubble. And maybe they'll behave differently. Each bubble will behave differently. Maybe. They will. I already know. I've done this before. They're very different. Oh, we wait. What else?
Do you mind if I skedaddle?
You should wait still. After the whole thing is done. So, the bubbles have grown, and I just want to check to make sure, I want to measure it again to make sure that our 2-to-1 ratio has kind of been, that it wasn't just an artifact. Now we're at 7 centimeters for the larger bubble, and 3.5 for the smaller. So there's still 2-to-1. Oh, the other thing is I chose test tubes that are the same size. They're the same like diameter, so I can just measure with a ruler, and that corresponds directly to the volume of the gas that's being formed. It's off? No, it's oh, the camera? Camera, why are you doing this to me, camera? It's off again.
It's not still recording.
Yeah.
I got storage.
No, it shouldn't be. Oh, I see.
What does polyatomic mean?
Many atoms. Now we're recording. Okay, so we have 2-to-1 ratio. We're just recapping. 2-to-1 ratio in the gas bubbles that have formed. It was on photo mode. I took photos of myself and not videos because I can't read icons apparently. All right, it's all right. I'll do this in period 7 also. Because I already did the fire one in period 7. All right, so for the next one, can somebody turn off the lights, the overhead lights? So the gas bubble from the negative terminal is almost to the end. So I'm going to do the splint test with it. So here we go. Oh, it kind of popped. It popped. Let's see it. There we go. It went pop. So the gas at the negative terminal kind of exploded. It was a small explosion. It was still an explosion. Still an explosion. Caught fire. And we're going to let the gas bubble on the positive terminal keep forming because we can't. Because we want to see what happens, and if like the more material we have to work with, or the more gas we have to work with, the easier it is to see. And the other wire is just in there. completing the circuit. In which we wait and wait. It's so much slower than the other bubble. Pretty good. I had some coffee. I did this demo, and also the fire one. Oh wait, no, I didn't do the fire one in the last, because like, yeah. So like, remember, like the power outage put this class period behind period one, but we'll catch up with this pretty much. We'll be on the same everything by next week. And we're pretty much down to where the electrode is, so I'm going to turn this off. And do our next splint test on the gas that formed at the positive terminal.
What's an electrode?
Oh, it's the wire going from the power supply to the wire. Good question. What's the electrode? So here we have our burning splint.
Is it gonna blow up?
We'll have to find out. All right. So we're gonna splint and whoa! It flared up. It burned more vigorously as it encountered the gas bubble. I'm using very specific language that may have appeared in a slideshow where it described experiments by a guy named Priestley, Joseph Priestley, who actually, as it turns out, did this exact experiment. And he described what he called the acid-forming gas. He also described what he called the water-forming gas. He named both of them in Greek. The slideshow didn't mention, I don't know why the slideshow didn't mention the water-forming gas. But,
You name them.
well, he named them in Greek. So, one of them was acid-forming, which is oxygen, and the other one is water-forming. In Greek, though. So, like, if you're hydrated, like, if you're drinking a lot of water, right? You're hydrated. If you have a dam on a river and a generator, that's hydroelectric, right? What else? So if you're making something, so like the hydrophobic is fearing water, hydrophilic is loving water. Yeah, like, because you guys all know Greek, right?
No. Just you can.
A little bit.
Harry.
The water forming.
Wait, can you actually speak Greek? Like,
I can like.
understand small time.
I can like look stuff up. I can kind of read. Kind of.
Oh, so.
It's hydrogen. Anyway, all right. And that's the demo. Hydrogen and
That's
oxygen.
it?
That's it. Yeah. The next.
Why not? What about the other?
No, like, no, what do you
What
do
about
with
the other one?
food
The
that
what
I-
other one?
The other? Oh.
The other, we already did the other one.
Oh.
I heard you get all that money.
There's the other.
I don't know.
Yes.